This section of the study guide is just practice predicting products of chemical reactions. We're going to do a lot of these together in class, but here's a good review. You may want to try some of these yourself and then go through the video and see if you're getting the right answers. You can just fast forward and pause so you can see the correct answers, or you can listen to it and get a little explanation for the correct answers. Now, as you do these, you're going to want a periodic table handy so you can find charges and write your ionic formulas. You will want your polyatomic ions handy so you can find their formulas and charges. You'll need your solubility chart, which can be used to find phase symbols. And you'll want your reactivity series to use in order to predict single replacements. So for example, this first single replacement is the reaction of chlorine gas being bubbled through a solution of magnesium bromide. It just means that the chlorine gas is reacting with the solution of magnesium bromide. My chlorine is diatomic gas, magnesium bromide is solution aqueous. It's a single replacement. I have a single element, chlorine, reacting with a compound. It's okay that the chlorine is diatomic. Chlorine's normal charge is -1. So since it's negative, chlorine is interested in switching with the other negative ion, bromine. I look it up on my reactivity series, and yes, chlorine is more reactive than bromine. This will work. So we switch the two. Diatomic bromine is liquid. It's one of the two elements that naturally occur in the liquid phase. And then again, if you're not sure of the phase for magnesium chloride, you can check the solubility chart. There is water present from the original magnesium bromide solution. So since magnesium chloride is soluble in water, it will dissolve in the water present from the original solution. It will be aqueous. And this reaction is already balanced. What a nice bonus. Number 2, dihydrogen monoxide is decomposed by means of an electric current. Well, dihydrogen monoxide is a fancy name for water, and it's being decomposed into elemental hydrogen gas and oxygen gas, both diatomic. We'll balance it. Good to go. Short and sweet. Three and 4 are both double replacements that involve iron 3 chloride. If you look up iron 3 chloride on your solubility chart, you should find that chlorides are soluble. There are a few that don't dissolve, but iron's not one of the exceptions. So the iron chloride is definitely aqueous. Number 3, we're going to react it with some sodium hydroxide, which again, if I check my solubility chart, anything with sodium is aqueous. So this is a double replacement that should work. I have two compounds, that's how I know it's a double replacement. And if I know that they're both aqueous, that means that they're willing to let go of their current partner and possibly accept a new partner. To form the products, I usually switch the two positives. You could also switch the negatives. It wouldn't matter. It doesn't matter what order you write your products in. But I should have sodium with chloride and then iron with hydroxide. When you write your products, you have to be a freak about charge. So there's only 3 chloride with iron because iron's charge is +3. On the product side, chloride is now with sodium +1. Subscripts do not get a ride to the product side. When you form the new combination of ions on the product side, check those charges to write the final products. And then obviously we need 3 chlorine in both sides, so we'll balance it with a coefficient. We should have 1 iron, 3 chlorine, 3 sodium, and 3 hydroxide on both sides. And then we look up the phases of our products. Anything with sodium is aqueous. Most hydroxides are not aqueous. Obviously, sodium hydroxide is. So the iron hydroxide is a precipitate. It should be a solid. Now in number 4, we're reacting our aqueous iron chloride with calcium sulfate. If I look on the solubility chart, calcium's not on there, but sulfate is. And actually most sulfates are soluble in water. There are a few exceptions, and sadly calcium is one. Calcium sulfate will not dissolve. So if it's a solid, it means that it's not going to let go of its current partner. Calcium and sulfate are not going to let go and take on a new ion to make new products. So this is your no reaction, a double replacement that doesn't work. Both reactants would need to be aqueous. Number 5 is a combustion. Liquid ethanol is burned in the presence of oxygen. That ethanol is a carbon compound, an organic compound, burning in oxygen. Combustions will always produce carbon dioxide and water. Sometimes by accident, people will put single replacement, and they'll try to do some kind of a funky switch. And I see how it could look like a single replacement. You have oxygen, a single element, reacting with a compound, but it's kind of a special situation where the organic is burning in the presence of oxygen. So your products are a no-brainer, carbon dioxide and water. Then all we have to do is balance. These are often exothermic, so the energy released is used to make this water a vapor. Now if you put water liquid, I wouldn't mark it wrong. But often in the lab, we would experience the water as a gas. A couple more that we can look at here. 6, 7, and 8 are all single replacements. Now, single replacements with water are kind of a special situation where we said use the water as hydrogen hydroxide. Calcium, my single element, is normally positive. And so it's interested in switching with the other positive hydrogen. I checked the reactivity series, and this should work. Calcium is more reactive than hydrogen. So we switch the calcium with hydroxide. We boot out the hydrogen. As an element, hydrogen is diatomic. And now here's the deal. That calcium hydroxide. Hydroxides are bases. So if we really go in the lab and run this, which we will, we can test our product to make sure that it is a base. It's just one of these kind of crazy reactions that you have to be aware of. When you put a metal in water, in a single replacement, that metal will only replace one hydrogen. You'll always get the metal hydroxide as one of your products. It will always be a base. The other product then is hydrogen gas. Now we probably know that the calcium metal is a solid, the water is a liquid, hydrogen is a gas, and then just use your solubility chart to find the phase of the calcium hydroxide. Most hydroxides are not aqueous. There are a few that do dissolve, but calcium hydroxide is not one of them. It's a solid. 7 and 8 are both single replacements with zinc. Zinc with hydrogen chloride, hydrochloric acid in number 8, and then zinc with sodium hydroxide in number 7. Zinc is normally +2. Now I probably would have told you that. Its most common charge is +2, or maybe you would have guessed that it's at least positive. So between zinc and sodium, if I check the reactivity series, zinc is less reactive. This should be a no reaction. And again, we're going to run a lot of these in the lab or in class so we can experience that it really doesn't react. But zinc with hydrogen chloride, zinc is more reactive than hydrogen. So this one should work. The zinc will replace the hydrogen. You'll get hydrogen gas and zinc chloride. And so again, you have to check your charges on the zinc chloride. This one should balance, piece of cake. And then to get the phase symbol of the zinc chloride, we can just go to our solubility chart. Most chlorides are aqueous. There are a few exceptions, but zinc is not one of them. So again, if these are going okay, maybe take a little time to try some of the rest, then bring back the next video and see if you are getting them correct.